that leads to what we call the Moody's chart. So let's see what we have gotten. What we are going to do is going to plot a graph of friction factor on y-axis and Reynolds number on x-axis, and we will do it in a log coordinate system. Okay, for laminar flow, F is equal to 64 by RE. So if I plot it in a log coordinate system, how would it look like? It will be a straight line of slope -1. So that's what is going to be laminar flow. Some, transitional Reynolds number somewhere around 2100, let's say, you will start seeing turbulent flow. We calculated an expression for turbulent flow, right? What was that? Some 1 by root F is equal to some expression we have calculated. You could plot that and you'll see a curve like that. Okay, so this is for laminar flow. That's for turbulent flow, but in a smooth pipe. What happens is that if you start incorporating the roughness factor, you're going to get curves like that. Okay, so this is basically, you go up in this direction, this is increasing the roughness. Okay, so this is, each of those curves would be corresponding to a particular value of epsilon by d. So such a diagram becomes very useful because then you don't need to remember any correlations. Just use that given Reynolds number, look at your friction factor and use them for your design. Okay, all the calculations that we have done in the last few classes is compiled into such a diagram. People have tried to come up, relations bringing everything together. One such useful expression, if you do not want to use the graph, is 1 by root f is equal to minus 2.0 log of epsilon by d divided by 3.7 plus 2.51 divided by Reynolds number based on d. This equation is also sufficiently good equation to calculate friction factor. Yeah. Yes, when I have written log, it is base 10. If I have written ln, that would mean natural logarithm. It is a general, people have tried to fit that equation and it reasonably reproduces the plot. So you could use either of them. Actually, you could use any of these things, okay? But whenever you are going to do a design problem, you do not want to stick to exact numbers. You would want to, say that, whatever number you get, you want to give some cushion to it. You will say, you'll take 15% or 20% extra, whatever is required. So there things get adjusted. So you could either use the equation or the graph. The graph is definitely going to be better. So let's move this chart. Next. So let's look at the flow, that we have had so far. We started with the laminar flow. Okay. Then we did turbulent flow in a pipe. Then we talked about roughness. Okay. So we are ready to do the next complication. What would be that in your opinion? What is, just imagine a real life scenario where you want to design a pump. Or, yeah, or a piping system rather. The next thing that, yeah. You said something, I thought, no? Power, yeah. So power we can calculate because once you know pressure drop, then you can just multiply it with the flow rate and you will get it. So no, we could encounter more scenarios. Okay, for example, so far we assume the pipe to be circular. It need not be circular. Okay, we may have a square pipe or a triangular pipe, especially for example, heat exchangers and stuff like that. You might have different cross sections. What do we do then? Do we do all the calculations that we have done so far for a different cross section? It becomes extremely hard. In fact, you can't even do that for many of the things. Okay, so therefore you define something called a hydraulic diameter. We heard hydraulic diameter, so that's where it comes. So we want to look at pipes of non-circular so to define it, we need to go back and look at how did we originally define our friction factor. We analyzed laminar flow in a pipe. We had some pipe, which we must probably would have drawn something like that, a circular pipe of radius r and let's say some length L with a pressure drop, let's say delta P at an angle theta and some delta Z, and if tau W is the wall shear stress, we would have written down some force balance. Can you check your notes and tell me what is the force balance that we wrote for this configuration? So there is a pipe, okay, and you have applied a pressure difference which makes it flow. It's inclined and therefore weight is playing a role, and of course the viscous friction is acting against it. So you need to apply, you can write down a pressure balance which would mean that if delta P into pi r square is the force acting along the pipe plus the weight, which would be pi r square times L times rho times G, let's say sine theta, should be balanced by the viscous friction that's acting on the walls, which should be tau W times 2 pi r into L. This is the equation that you might see in your notes. Okay. Now what we want to do is we want to write down a similar expression for a non-circular pipe. Let's say some non-circular pipe. Some shape. Okay. Everything else remaining the same. You can write. So let's call this has an area of A, and so A is the area and P is the perimeter. You can write down the same force balance as delta P into A plus, this we must have simplified, no? L times sine theta would have given you a delta Z. So A times rho G times delta Z is equal to tau W into P into L. Just generalizing it in terms of A and P. Okay. One thing that you need to be careful is that when we talked about the circular pipe, okay, the wall shear stress was a constant quantity. It doesn't matter where you are actually looking at or where you are calculating tau W, because nothing was changing along the theta direction or Z direction. But that's no more true when you talk about a non-circular cross section. Depending upon where you are looking at, tau W could change. So we can say tau W is some average tau W that we have calculated. Yeah. So that would mean delta P plus delta P, let's say, divided by rho G plus delta Z is equal to tau W bar L there divided by rho G. So what you see on the left hand side is what you originally had. Now you end up with an expression which contains tau W, area and perimeter and so on. And this quantity is what is called hydraulic radius. In other words, RH is nothing but cross-sectional area divided by vector perimeter. And that's actually for a circular pipe, that will be equal to R by 2. Right? So one can define a hydraulic diameter PH is equal to 4 times cross-sectional area divided by vector perimeter. So that PH is equal to P for a circular. So in case of a circular pipe, we wrote HF, the head loss, is equal to friction factor times L by D, V square by 2G. In case of a non-circular pipe, we'll write a similar relation. HF is equal to F times L by D hydraulic, D average square, D square divided by 2. Everything that we did for the circular pipe, we just borrow it, but replace all the diameters with the hydraulic diameter. So for laminar flow, we had F is equal to 64 by RE for the circular pipe. Here we will define F is equal to 64 divided by REH, or rather PH, where the Reynolds number is now defined based on the hydraulic diameter. So REH is PH times B times rho divided by mu. For turbulent flow, we will get some relation containing Reynolds number, friction factor, epsilon by D equal to 0. Here we will use the same relation, but we will use Reynolds number based on dH, F epsilon divided by dH. So what I'm saying is that everything that you have done so far, we will just borrow the same framework. We'll just replace our all diameters with hydraulic diameter. Assume that that's going to work. If you have wondered how good it is, this relation is found to give you things with an error of 40%. Huge. This relation seems to give approximately 15% error. Of course, depends on what kind of geometry and so on. Okay, so these are definitely not good relations, but we do not want to do, elaborate calculations for any other geometry. Just use the same framework. Questions? Yeah. Let's say you have a fluid that's flowing between two pipes. Have you already been, you did heat transfer? Shell and tube heat transfer and heat exchanger and so on. Huh? So imagine you have a fluid that's flowing between two pipes, okay, and you are interested in calculating the pressure drop for the fluid which is between in the gap in the annulus. What would be the hydraulic diameter? It's going to be 4 times cross sectional area by vector perimeter. So now you see, right, where is cross-sectional area coming from and where is vectored perimeter coming from? Cross-sectional area is coming because that's the one which is going to multiply with your pressure drop. Vectored perimeter is coming because that's where your shear stress is acting. Okay, so it's really that ratio. What would this be? 4 into cross-sectional area is pi into Rho square minus Ri square divided by vectored perimeter would be 2 pi Rho plus 2 pi Ri, right? Both inside and outside, both the cylinder, both the surfaces will generate, exert the shear stress. You can simplify and see what you get. So that's how you should do the calculations.